Hello everybody, this is Mesa Mer Aran. I'm from Ozen Engineering and I've been at Ozen for a year and a half, and before that I was in an electric car company called Byton, and before that I was 5 years with Ford Motor Company. This is the fifth turbo machinery YouTube short. This is mostly going to focus on solution setup, which is done in CFX Pre. A little about us. We are the early channel partner ANSYS in California. We have 17 years of successful operation in the Bay Area, 1,000 plus happy clients. We have good amount of expertise in multi-physics finite element analysis, or FEA, expertise in computational fluid dynamics, or CFD, and also on top of that electromagnetics, which covers both high and low frequency. Our territory includes, of course, Oregon and California and Nevada. As you see, the headquarters in Sunnyvale, and then we have an office in Portland, Oregon, and also some staff in Long Beach, California. This is the list of softwares we can sell to you. Under structures, we have Mechanical, Encode, LS-DYNA. On fluids, we have CFX and Fluent. On electronics, we have high frequency and low frequency categories, which is FHSS and Maxwell and a lot more. And we have also some tools on semiconductor and optics. On the material side, we have Granta. On embedded software, we have different packages, SCADE, and on system analysis, we have TeamBuilder and Medini. So whatever industry you're at, probably we have some tool that can make your job easier or more efficient. Feel free to give us a call, and we'll be more than happy to guide you to the right tool. To go over the solution setup, we went through a couple of YouTube shorts before, and we went all the way till meshing. So we created an initial design or conceptual design, and then we brought it into Workbench and meshed that with TurboGrid. And then now we got to do the solution part. Solution usually is done in CFX Pre. That's the preferred tool, and they mostly use rotating frame of reference, or RFR. In some tools like Fluent or IcePack, sometimes they call it MRF, which is pretty much the same thing, which means that you sit on the rotating reference like the blade itself, and then based on that, you solve the governing equations. The benefit of that is simplifies the problem because it changes a transient problem into a steady state problem. We are not going to go too much into technical details of it. There's not much time. To set up the CFD model, we need to define the fluid domain, which means we got to define fluid material properties, domain motion, and also the physical models that we are going to use, such as turbulence model, heat transfer model, etc. And after that, we do define the boundary conditions and solver settings and a couple of monitors to check on convergence, and finally we would run it. For domain setting, we need to define its rotating. We need to set the angular velocity and also the rotation axis. And also we need to define material properties and also reference pressures. For modeling turbulence and heat transfer, definitely SST and total energy with viscous work are the preferred methods for turbo machinery. This comes from several years of experience in different industries, and these are the best practices that ANSYS provides. And for the boundary condition, we usually have a passage because the geometry is mostly periodic that we're dealing with. There's an inlet and outlet, and also there is hubs and blade, which is also like a no-slip valve, and on the right and left you have the periodic interfaces. The good thing about CFX is that it has a turbo mode, so it does a lot of its things automatically, which makes your job way easier. So we're going to see the tool. I think this is the file we worked with in the last YouTube shorts. We generated the geometry for the impeller and also stator inside the CF turbo. We brought it into TurboGrid and mesh that. Now the next step is that to solve it. So we go to transfer data to new CFX, and technically we can drag and drop also this term. So you have both parts, but just for the simplicity, we just model the rotor for this case. So you open CFD, CFX Pre. Here you see that. You can manually define all these boundary conditions, as I mentioned in previous slides, but there is a simpler way to do that. There is a tool for it. You go Tool, Turbo Mode. First, it's asking what are you dealing with, what's the machine type you are trying to model. You say, okay, it's a fan, an axial fan, and it has defined the z-axis, and the solution is steady state. You click Next. This is R1, which is this whole area. It's rotating. You say, what is the RPM? Let's say you define 376 RPM. You can put any value you want, and then just define it. That easy. Then you push Next. So what's the fluid? Of course, for fan, I would say you can choose air. That's a good approximation. And what are the boundary conditions? You can put different values, pressure inlet, outlet. I will say, let's say pressure total inlet and mass flow outlet, just to put some values on it. But you can choose whatever is more correlated to your model. You have different options for, let's say, heat transfer and turbulence. You can choose anything that sounds more relevant to you. And then you have the periodic boundary condition. As you see, these are the interfaces. These two walls are the periodic interfaces, which is already detected. You don't need to do anything manual. And then these are the other boundaries. Blade, which is a wall, hop, which is again a wall, inlet, which is inflow, and outlet, which is outflow, and the shroud again, which is a wall. So as you see, quite straightforward. It just happens automatically for you. And then after that, enter general mode. You don't have any options on that. Just finish. You're pretty much all set. As you see, the interface has been placed. The boundary conditions have been placed. I think you don't need to do anything else. Just for the solution output, maybe we need to put a monitor to make sure we are seeing the convergence properly. To do that, I create, let's say, pressure outlet, P out, to see if the convergence has been achieved. And we define expression for that. We simply can say, for example, the mass flow average pressure at the outlet. To do that, it's quite straightforward. So I look at mass flow average. Pressure at R1 outlet. That's simple. You click OK, and you have this monitor set up. You can put anything else that you're interested in to just monitor it and see how good it converges. And you're all set. Save, close. You can definitely run this model. Okay, it's done. Now you go to solution. Sometimes it needs a little patience. It's working though. Okay. We are here. Just select Devil Precision, Intel Parallel, 2 cores. You can start to run. As you see, the process is pretty straightforward. So if you're interested, you can even do it manually. If you have different parts or different meshes that merge into together, you can bring it in separately, and then you might need to create an interface in between in more complicated cases. And pretty much it's similar. As you see, it's iterating, it's going toward convergence. Everything is going down. there will be some oscillation and then it flatten out. I don't have that much, I mean, we don't have that much time to wait for it until the convergence is achieved, but I will say it's like a 20-minute run or so. And this is the end of the current YouTube short on how to run a thermal machinery case in CFX. Okay. Thanks for your attention. And if you have any questions, I will be more than happy to answer. Thank you and have a great rest of the day. Bye.